On the left, we have, once again, the multiplicative tables mod 7 and mod 8. And recall that in the case of mod 7, all the rows were good, and in the case of mod 8, certain of the rows were good. And I've ticked the relevant rows here. So all the rows in the case of mod 7 and 1, 3, 5 and 7 row in the case of mod 8 are good. And by good we mean that the row itself, as here, is a permutation of the top row up here. And in particular, in any good row, the number 1 must occur, so that if row 5 is good, as it is here, then 5 will have a multiplicative inverse, namely something which when multiplied by itself gives me 1. In this case, 5 is its own multiplicative inverse. Up here, we look at row 3, for example, it's good, as are all the rows here, and 3 times 5 is 1, so the multiplicative inverse of 3 is 5. So we can now formulate a theorem as follows. Assume that n is bigger than or equal to 2 is an integer, that a is in 1 up to n minus 1, and the greatest common divisor of a and n is equal to 1. Then we have the conclusions, which I just stated before, namely that the row corresponding to a, so a with 3, it will be this row here, which is 3 times 1, 3 times 2, 3 times 3, up to 3 times 7. In other words, row A is a permutation of 1 up to 7, or more generally, 1 up to n minus 1. And A will have a unique multiplicative inverse. So just to reiterate, the hypotheses of the theorem are satisfied for all rows in case n equals 7, in the case n equals 8 for the rows 1, 3, 5, 7, and if n is any prime and a is in 1 up to n minus 1, then certainly the greatest common divisor of a and n will be 1. In the next slide we will prove part 1 of the theorem, which says that row A is a permutation of 1 up to n minus 1. And in particular, part 2 of the theorem follows immediately because 1 must occur in the row corresponding to A exactly once, and then that gives us the element B, which when multiplied by A is equal to 1. So now we'll go through the proof of the main part of the multiplicative inverses theorem, which is part 1. As we saw before, part 2 follows immediately. The result is that if I consider any mod n multiplication table and any a between 1 and n minus 1, such that the greatest common divisor of a and n is equal to 1, in other words, such that a and n have no common factors, then the row corresponding to a is a permutation of 1 up to n minus 1. And I've checked here the relevant rows, which is every row in the case that n is equal to 7, and the rows 1, 3, 5 and 7, which are the relevant rows in the case of the mod 8 multiplication tables. And of course, for all those, as we see, the conclusion of the theorem holds in that these rows are each permutations of this row here in the case of mod 8, and similarly in the case of mod 7. The first step in the proof, and the major step, is to prove that for every b, every number b in the range 1 up to n minus 1, there is some k in 1 up to n minus 1 such that b is equal to a times k. In other words, a times 1, a times 2 up to a times n minus 1 give me all the elements in the row A, and I want to show that there's some element, so it'll be a times k, for some k between 1 and n minus 1, which gives me b. So I want to prove this for any b. So here's the proof. The main point in the proof is to use the Euclidean algorithm, which says that if the greatest common divisor of a and n is equal to 1, then we can write 1 in the form SA plus Tn. Next, we multiply through by b, and we get that b is equal to SAB plus T times NB. Now this is good news, because what's happening now is that since we're working modulo n, this term here is going to be 0, mod n. And this looks very promising. It's telling us that b is a multiplied by SB modulo n. And this is very close to what we want here. So from this, working modulo n, we get that b is congruent to SAB. And because we're interested in multiplying numbers from the mod tables, I'm going to replace S by S bar, where S bar is chosen between 1 and n minus 1 so that it's congruent to S. So now what we have is that B is congruent to S bar times AB modulo n. And all those numbers, S bar, A and B, are in the range 1 up to n minus 1. Because we assume that A is in the range 1 up to n minus 1. We assume B is in the range 1 up to n minus 1. And now we've got S bar in the right range. This number here is itself a number between 1 and n minus 1. And it's obtained by multiplying A, S bar and B and taking the remainder modulo n. So this is just that number, SAB. We've just put things in a different order. So if B is congruent to that, then that means B is congruent to this, because this is just the remainder after dividing that by n. So now we have that this number B is congruent to this number, modulo n. But remember, this number and this number, they're all in the range 1 up to n minus 1. So therefore, this must actually equal this. And this proves the claim. B is equal to A times K, where K is equal to S bar times B. So from the claim, we have that each of the numbers 1 up to n minus 1 occurs at least once in the 8th row. This here is the 8th row. So this row has n minus 1 numbers in it, but each of the numbers 1 up to n minus 1 occurs at least once. So therefore, each number from 1 up to n minus 1 must occur exactly once. So in other words, this row is a permutation of the numbers 1 up to n minus 1, precisely because each of those numbers occurs in this row exactly once. And that's the proof of the theorem.